Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration. Hi there, and welcome to the 9th episode of Cyclopod. It is late March, and therefore we are just a few days past the vernal equinox or the springtime equinox. So a quick reminder, what is an equinox exactly? The equinox is the time at which both hemispheres are receiving the sun's radiation equally. Solar radiation is falling perpendicularly onto the equator, and thus on that particular time of the year, there is no hemisphere tilted towards the sun. There is no summer or no winter hemisphere. An equinox occurs twice per year, at the end of March and at the end of September. Now imagine the effect of precession on top of that. Once every precession cycle, it will be the case that the March equinox or the vernal equinox occurs exactly at the same time as perihelion. So Earth would be close to the sun during the vernal equinox. That means that at the equator, the incoming solar radiation at the end of March is very high. First, because the sun is directly overhead during the equinox. And second, because the Earth is close to the sun. The Earth is in the perihelion at the same time as the equinox. Now imagine that we go 11,000 years further in time. So we go half a precession cycle further in time. Then the Earth would not be in the perihelion in March during the vernal equinox, but it will be in the perihelion in September during the autumnal equinox. But of course, the effect on insolation remains the same. At the equator, the incoming solar radiation is very high in late September, firstly, because the sun is directly overhead in the equinox, and secondly, because the Earth is close to the sun, the Earth is in the perihelion in late September. So if you are at the equator, you get maximum insolation not once per precession cycle, but twice per precession cycle. Once insolation is maximized in March, and once it is maximized in September. Now, this is an interesting characteristic of low latitude insolation patterns, and it has been used to explain half precession cycles in tropical sedimentary archives. However, whether half precessional cycles can also be detected at mid and high latitudes, that has been a topic of much debate. Now, Arne Ulfers just published a paper in Quaternary Science Reviews that sheds new light on this question. Arne, very welcome to Cyclopod. Tell us, where did you find half precession cycles?
Yeah, hi David. Thank you very much for having me in this podcast. I'm very happy to tell you about my latest research. So the focus of this paper is Lake Ohrid on the Balkan Peninsula in southern Europe. And this lake is located in a tectonic basin, which is directly on the border between Albania and North Macedonia. And today the climate is mainly dominated by the Mediterranean climate. So we have hot and dry summers and rainy winters. But also other systems such as the Siberian High, the North Atlantic Oscillation Modes, and the monsoon systems influenced that region. And there are already several publications about this lake, and even one of my colleagues published a cyclostratigraphic analysis of the youngest part of the sediment sequence from that lake. However, when my colleagues and I started to work on the complete sequence, we found that besides these classical Milankovitch cycles, there are also other signals in this data.
All right, interesting. So if I understand it correctly, Lake Ohrid is not a dried up lake. It is filled with water. Hence, I assume you haven't been working on outcrop material where you would have access to dried out lake sediments. How did you get to your material?
Exactly. Lake Ohrid is a recent lake, which is and was filled with water for the last 1.36 million years. And as a recent study shows, never dried up during that time. This means that we have a continuous undisturbed sedimentation process for the last 1.36 million years. The sediment sequence we were looking at is from the central part of the lake. The drilling and coring was conducted as part of an ICDP project in 2013. And at this particular site in the central part, the total core length is almost 570 meters and consists mostly of fine-grained lacustrine muds. The project team itself consists of more than 40 scientists from 11 nations, plus lots of technical stuff. Up to date, there are several publications about this specific core and about Lake Ochot in general. And concerning the sedimentology, we can say that we basically have a two-component system. Firstly, we have clays with relatively high amount of detrital input. This was deposited in glacial periods. And secondly, clay with relatively high carbon content from interglacials. And this is due to the hydrology of Lake Ochot. The lake is mainly fed by another lake through a karst system, and that water from the karst system has to pass a limestone mountain range. So in interglacials, when the climate is warmer and wetter, more water and thus more ions are supplied to Lake Ochot, and we find higher carbonate contents in the sediments in interglacials.
And your aim was to identify and to understand the half precession cycle signature at Lake Ohrid, correct?
Yes, we investigated the half precession signal in various sedimentary proxies from Lake Ochot, and we observed changes of the half precession signal over time. But the investigations in Lake Ochot were only the first step. We included various other proxies from different sites in and all around Europe. And we did this to find regions where the half precession signal may be more or less prominent than in Lake Ochot. And we hope that when we put all this information together, we would get a clearer picture of the half precession over time and space.
Yeah, cool. That's interesting, that spatial connotation. What makes that Lake Ohrid is so well suited and so interesting for answering your research questions?
As I mentioned before, Lake Ochot is quite old for a lake and has a continuous sedimentation with no hiatus in the sedimentation sequence. This is an advantage for cyclostratigraphic analysis in general, and further, the sedimentation rates are quite high. They are almost 35 centimeters per 1,000 years, which means we have a good temporal resolution in the sediments. And then we have a whole set of proxies to choose from. These range from pollen data over chemical information, such as total inorganic carbon, and we even have downhole logging measurements. The latter were measured by the Leibniz Institute for Applied Geophysics and were the trigger for the publication because we observed the half precession cycles in there for the first time. By the way, the criteria I just mentioned also apply for the other datasets we used from and all around Europe. And this is not at all self-evident that one can find datasets that span 1 million years, that have a sufficient resolution, are continuous, include climate-sensitive proxies, and are available to the public as well. So that was not that easy.
I can imagine. So in the first part of the podcast, we described your ICDP drill core from North Macedonia and Albania, spanning the last 1 million years. Now, in the second part of the podcast, I would like to discuss some of the more technical aspects of your work. You start off with a wavelet analysis of your proxy records, and you notice that half precession cycles are more pronounced during interglacials. But you also mentioned that wavelet analysis is sometimes challenging to interpret when high frequency variability is too large.
Yes, in the very beginning, we were looking at the original data and thought that we could identify peaks at exactly the position between two precession peaks in the records and in certain parts. And then we looked at amplitude spectra to see if there are significant peaks in the bandwidth of half precession. And they were there. So not as clear as the classical Milankovitch cycles, but we saw the half precession cycles in the amplitude spectra, and that gave the first evidence. And then we used the wavelet analysis that you mentioned in your question. So this way we could observe that the half precession changed over time. And roughly spoken, we observed that the half precession signal is stronger in interglacials and stronger in the younger parts of the records. However, the records have their individual challenges, for example, regarding the proxy sensitivity to climate change and resolution, but the general pattern was clear with the higher half precession in interglacials. Nevertheless, we wanted to determine more precisely how clear the half precession signal is in the different records in order to compare them. And for this, we needed a quantitative method to determine the clarity of the half precession signal.
All right, that makes me very curious. What kind of technique did you use then to determine the clarity of the half precession signal?
First, we filtered the data so that only frequencies in the range of half precession remained. And if you compare the filtered signal with the original data, you can see a correlation with the naked eye sometimes even. But we determined a correlation coefficient between these two data sets. And the higher this coefficient is, the clearer is the half-precession signal. And with this, we were able to show quantitatively that records from the regions in the southeast have a higher half-precession signal. And in addition, we extended this method and applied a sliding window approach. This means that a window with a predefined length, in our case a time period, passes over the record and estimates the development of the half-precession over time. And this allowed us to show that the clarity of the half-precession signal increases towards the recent.
And so that technique basically also confirmed what you had already observed with wavelet analysis, namely that half-precession cycles are higher amplitude during interglacials?
Yes, and that the half-precession signal increases towards the recent. In addition, we could quantify the clarity of the half-precession in the different records and compare them.
So if I hear that, then half-precession amplitude is very similarly behaving as precession amplitude. And therefore, one would expect a positive correlation between the amplitude of half-precession and eccentricity. But that is not always the case, right? You check this relationship for several records, and for some of this holds, and for others it doesn't?
Yes, we see a connection of half-precession to eccentricity cycles, both the 100,000-year cycle and the 400,000-year cycle. But as you mentioned, only in a few proxies, and it's not very distinct. And this is one of the things that definitely needs more investigation and may be solved when we investigate records which go further back in time.
It's time for the number of the month. This month, the number is 26. The ICDP program, the International Continental Drilling Program, which drilled Lake Ohrid, is now 26 years young. Therewith, ICDP is significantly younger than its sister program IODP, the Ocean Discovery Program. However, while IODP is really on a pivotal moment in its history, ICDP seems very active and full of energy. How do you look at that, Arne? How do you see ICDP evolve in the next years and decades, and which big questions could we soon answer by means of continental drilling?
It's good that you mention IODP and ICDP in the same sentence here already, because this is where I see the future of scientific drilling. The combination of marine and terrestrial environments will give a broader view on paleoclimate research questions. I mean, what we did, for example, in our study was to take IODP data from Project A and ICDP data from Project B and compared them. And many others do this as well. But this is not what I mean. I think it will be really advantageous when proposals and drilling projects are from the very beginning designed to link terrestrial and marine environments. Some of this is already happening right now, but we need to expand these ideas and should not see the terrestrial and the marine environment as separate parts or two different worlds.
That's true. Amphibious projects are the future. Okay, back to the science now. I want to know, Arne, whether you think that half-precession cycles just didn't happen during glacials, or are they just simply less pronounced and therefore harder to detect?
This is a very good question. And of course, the Earth's orbital parameters did not change in glacials or interglacials. What I think is, as you already mentioned, the half-precession signal is less pronounced in glacials and thus harder to detect. But there are several reasons why this is that way. We can argue that during glacials, the general climate variability is lower and thus changes as response to orbital forcing is weaker. And we did, in fact, analyze various proxies. Some of them are just not capable to record any signal in glacials or in interglacials. We always need to keep things like that in mind and investigate individual records with individual approaches. And the best proxies for this kind of investigation exhibit climate variability in warm and in cold periods.
It also seems that half-precession cycles are more important after the mid-Pleistocene transition as they were before. I know your records do not go much further back in time than 1 million years ago, but can you speculate a little bit about this?
Indeed, this is a feature we pointed out in this paper. It is really difficult to make statements about the half precession before the mid-Pleistocene transition. As you said, this is all speculation. It could be that the half precession is of less important role during or before the mid-Pleistocene transition. And we know that the glacial interglacial variability was dominated by the 41,000 obliquity cycle back then. In our study, we showed a suspected connection of the half precession to eccentricity, but no connection to the obliquity. So it might be that in a 41,000 year world, the half precession is weaker, but again, this is only speculation.
Well, someone needs to investigate that then. Another interesting observation in your paper is that clearly the records from the southeast, so Lake Ohrid and the eastern Mediterranean, they have a stronger half precession imprint compared to the records from the Iberian margin and especially the records from Greenland. What does that tell us about the connectivity of the climate systems? Because that was your main research question after all, right?
Absolutely. That was one of the major questions. If and how we can use half precession signal in a paleoclimate context. So in the beginning of this episode, you described very well that half precession signal is most relevant for the tropic region. So if we assume, and many other authors support this assumption, that the half precession signal is of equatorial origin, how is it possible that we observe the half precession signal in Europe then? The answer to this is the connection of the climatic zones through environmental processes. And I can explain this very well using the Nile River as an example. When we have increased monsoon activity in low latitude Africa, the Nile responds to that and transports information about that northwards into the Mediterranean. And it is such mechanisms that can transport also information about the half precession signal from the equator to mid and high latitudes. And if we follow this idea, the half precession signal becomes weaker the further we move north. And that's exactly what we see in our data. If we observe an increased half precession signal in the mid and high latitudes, this may be an indication for the connectivity between climate zones in the past.
Thank you, Arne, for running us through your recent paper. As you know, I usually work in much deeper time, where the level of detail and the number of available records is usually quite a bit lower. However, from reading your paper, it becomes clear that we still have quite some fundamental work before us before we understand Earth's climate variability on Milankovitch and sub-Milankovitch timescales, even for the late Quaternary. I especially remember that Arne demonstrated that half precession cycles have a tropical origin, but they can be transferred through higher latitudes through climatic teleconnections. For example, through water running through the Nile runoff, connecting the African monsoon with the Mediterranean. From there, it can be transferred even further north through interactions between the Mediterranean sea surface temperatures with the atmosphere and through the Mediterranean outflow water into the North Atlantic. All very, very exciting. Thank you again, Arne. I also would like to thank you for listening and see you next time.